everybody. Can you all hear me? Good? A little bit? Okay. Hi, I'm John. Like Sweeney said, I am on the real-time platform team. Apparently, I'm a senior software engineer. Who knows? On the slide are a couple of ways you can yell at me. I can also post them later if you like, if you have questions or comments about the talk. So tonight is basically distributed systems disasters. So I imagine a lot of you work with distributed systems. They're taking over the industry. They already have in a lot of ways. And we run distributed systems on a reasonably large scale. I'll talk about that in a second. Several thousand machines, several million requests a second. So I like to think that we have some good disaster stories. And I'll share probably 4 or 5 of them with you tonight. I'm going to talk a little bit about where we are architecturally, how we got here. A lot of the answer to that question is by accident, and whether or not we actually like it here. So there's still stuff we want to change about our systems. This is the canonical diagram of the AppNexus real-time platform. And it's very complicated, and I'm not going to talk about it. But for some context, the only web-facing thing we run is an application called ImpBus. It's Impression Bus, if you want to say the whole name. And what it does is act as an auction router for ads served on the internet. Like Sweeney said, we serve ads on the internet. And that is fundamentally what the real-time platform does. And it has several steps. This is actually not the complete diagram. Basically, we get a request in from a web page or a supply-side platform, maybe another ad exchange. We take that and we collect some more user data about the request so that we can kind of enrich the value of the auction through our own system called Cookie Monster and some data providers that are external to AppNexus. We might have a price provider in there somehow telling us how to bid or what to bid. And then we send and receive bid requests. ImpBus is a sell-side platform, and the bidder is a buy-side platform. That was a decision that was made very early on in AppNexus's history. At first, the buy-side platform didn't exist, and it was just ImpBus. But then a little bit later, we built a bidder, and they're separate applications. So there's very little crosstalk between instances of the same application on our stack. An ImpBus generally doesn't talk to an ImpBus. A bidder generally doesn't talk to any other bidder. ImpBus to bidder and back, and that's it. Once we've gotten a bid response, ImpBus can actually send an ad back to the page. And that's listed as 7, but it can actually happen before some of the logging, which is 6 in this case. So once we've actually served an ad, no one's gotten paid yet. The liquidity of the ad markets that we run depends on people getting paid. So we log a lot of transaction data to a thing called PackRat, which there was actually a previous tech talk about, and is basically a log router, shuttling things to a giant data pipeline that, for the purposes of fitting on a slide, I've just represented as a database. Finally, it's a lot more complicated than that, and we've done a lot of other talks on it, so I won't go into it. Also, I have no idea how it works. I'll be honest about that. So finally, in terms of what to bid and what we can bid on, we have a system called Batches that basically creates and maintains an in-memory database in both ImpBus and bidder. In terms of the list of campaigns that we have, ad campaigns, what tags we're serving on, things like that. And Batches works by every couple of minutes, taking essentially a diff of a MySQL database and distributing it to our applications, ImpBus and bidder. So ImpBus and bidder are the 2 main things that we're going to worry about in terms of reliability and performance, because they're really what allow us to function as a company. And we do this kind of fast. Actually, I missed saying that all of this is supposed to happen within 120 milliseconds. If it doesn't happen within 120 milliseconds, I've failed at my job, and so have some other people in this room. So we try to make this fast. It's not like high-frequency trading speed, but it's certainly not slow. And we do this a tremendous number of times per second. This is a recent graph, so 324 is the thing at the bottom right here. We're doing roughly 2.2 million requests a second at peak right now. And I think we're probably at peak right now. So the scale is not small, and the deadlines are reasonably small. And the downside is that it's all in C. So there are upsides and downsides to this. The legacy reason is that the founder of the company, Brian O'Kelly, knew C when he started it. There are other reasons, mainly that the only other two real language options at the time were C++ and Java. C++, you already know C, you don't really need C++ in that case. And we can debate this later if you want, Paul. But Java was not really mature enough at that point. This is 2007 we're talking. So we went with C. And that brings all of its little baggage with it. So what we're going to talk about tonight are data distribution reliability, traffic availability, performance across networks, and C struggles. So I mentioned C. We're going to talk about it. It's going to be a first-class citizen here, and it's kind of a tenet of our platform. But let's start with data distribution, and we need a little context for this. So our IMPUS and bidder applications are architected roughly the same way. In 2009, they were all separate processes on every core. So every process had its own core. We would run, I think we had 8 core boxes at the time, 8 processes per box. And each of those processes would load in their own set of batches data. So in-memory database, list of campaigns, list of tags. And then they would all listen on port 80 through an actually separate application, which was a router, which we got rid of. I've omitted that. They'd all listen on port 80 and do work. The downside to this is that when you get that like hockey stick growth that startups get sometimes when they do well, either by hook or by crook, you have to run 8 copies of your in-memory database on your single box, which is bad. So this got worse and worse and worse, and we kept finding like hacks and ways to optimize memory usage. And I wasn't even there at this point, but I've heard about it while drinking. Got worse and worse and worse. Couldn't find any more efficiency gains to be made out of our in-memory database. And so we went to multi-threaded single writer. So threads instead of processes share memory. The downside to this is that you have to synchronize on that memory. So now we have a single process with worker threads and a single batches thread, also running control applications. So they all listen on port 80, and that's great. It works pretty well. Memory usage is solved. It's actually, of course, it climbs back up once you have more growth, but that solved it immediately. And this happened in about 2012 or 2013, depending on the application. So 2014, I'm on Pager. I started in July 2013. And it's like January, my first time, I think, on Pager by myself. It's like a Sunday night. I'm looking at my computer, and I'm actually watching the status dashboard on a Sunday night at 9 p.m. because I had nothing to do. And I see that we all of a sudden go from green to yellow to red. And this is IMPUS. This is the web-facing architecture for AppNexus. So if it's down, that means we're not serving ads. It means that no one can talk to us, and it means that we're not talking to anyone else, because it's the only thing that talks to the outside world. If bidder goes down, it's somewhat easier because we can still talk to external bidders. But IMPUS means that we're gone from the internet. So we hit 0% up at one point. And at that point, I was kind of shaking a little bit, because it's on me at that point in time. And I know this happened because I created the ticket and I was assigned to the ticket. So that's great. How do you fix it? You're down on a Sunday night. Everyone's having dinner with their families or something. Okay, so I mentioned multi-threaded single writer, and this becomes important because if you distribute diffs of your database every 2 minutes, and this was actually a selling point for us. We could update business objects on the system within, say, 2 minutes. You distribute good data in 2 minutes, and you distribute bad data in 2 minutes. So if you distribute, say, a double delete, and you're not expecting it, the single writer thread crashes the entire system instantly across all of your applications. So all of a sudden, you go from 100% up to 0% up within like 2 minutes. It's worth noting that I get an email every time one of our systems crashes. Like any box component of any system crashes, I get an email. So I got like several hundred emails in like 2 minutes, which is great. It turns out this is the backtrace for this crash. It's a double delete, so we got this object called member data access segment. We called the receive function, we called a delete function, and that crashed. So that's great. At this point, our single writer thread has brought down all of our worker threads, so we're completely lost to the world. And we actually caught this within 4 minutes. 2:11 UTC, 100% down in SYN1, AMS1 Frankfurt, and 90% down in the other 3 data centers. So we're effectively gone. Within 4 minutes, we were looking at the problem, but you notice at the last timestamp there, we weren't actually totally back until the end of the hour. So that's not great. When you're trying for 4 nines of uptime, an hour to fix a problem is not great. And the problem with just instantly restarting your apps is that when you start up in this world of applying a diff to get to the latest state in business object history, you have to apply a state of the world file when you start up, and then all of the previous diffs, and then you can start going. So that brings your in-memory database up to speed, and you can start serving on business objects. The problem with that is that if you crash on one of these diffs, and then you restart, you have to replay all the diffs. So you're going to crash again. And so really, in this case, we had to patch our code before we could actually come back. And this is a problem with a lot of distributed systems, not unique to us, but it plagued us for the first several years of our company life. And this is a failure of validation engines. So in like 2010, we had this problem, maybe 4 times in a week or something, where we'd crash and go down. So we said, we need to validate these diffs before they go to production. So the batches system is going to send the diffs to a copy of the prod app that's not actually getting traffic. And before it distributes that data to the rest of the production plant, verify that everything's okay. A, that it didn't crash, and B, that it said, I think I'm consistent. So that's good. That VE responds, okay, I'm happy. And then we send the data out to the prod apps. In 2014, we had the system running. And it's not because the validation engine as an idea failed, it's because we failed to keep the validation engine in sync with production. So even if you have an architecture that scales really well, you have a VE that's out of sync with prod for like 2 hours and you crash anyway. So that's awesome. But this crash is indicative of like early AppNexus teething pains. So single writer is great for a variety of reasons. It crashed us in this case. It makes lock-free data structures really simple, or simpler, and it makes our threading model simple. So if you're not the control thread, you're a worker thread, easy. This was made by necessity because we just needed threading. We needed threading really fast to get over our memory issues. But it turned out pretty well. Lock-free data structures are a lot easier to write when they're single producer. And most of our core data structures now are lock-free, which is fun. We only have like 4 or 5, so it's easy to make them lock-free and like test them really well. Yeah, until you screw up. So we have data distribution crashes, which I just talked about, and we have traffic crashes. And traffic is sort of fun, which we'll talk about in a second. The single writer can bring down the world. In this case, in this previous crash we were talking about where we got a double delete, we wanted to basically turn back time. We wanted to start up and not apply the diff that crashed us, because everything was fine until then. We want to apply the stream of diffs up until the point where we know we crashed. So say at hour 4 we crash, let's rewind time to hour 3 and not distribute any data past hour 3. We'll come up with old data, like we'll start up and the business objects will be wrong, well, old, but we'll be up and we'll be serving ads. So this thing called maxTS is what we implemented as a result of this, and it prevents distribution of our business object data past a given timestamp for the entire plant. So it works pretty well. Once you see a crash that brings down the entire plant at once, rewind time a bit. When you come back automatically, you'll still come up and you'll be serving traffic again. So you're maybe down for 10 minutes instead of an hour when you have to patch your code. Traffic crashes. So we just talked about crashes on the batches thread, on the database thread. Now we can talk about crashes on the traffic worker threads. Of course, again, we're single process, so any crash on any thread can bring down all the other threads. And this is an example of what happens when someone turns on a piece of traffic that you weren't expecting. These are our 2 US data centers in purple and red. And all of a sudden, at like 1945 UTC on this day, they went to 50% of their traffic load. So we lost half of each data center at peak, basically, which is really bad. I was also on call for this one. I've picked crashes that I have some like personal grief from. And if you're a client and you're in this room, you've probably seen the results of these in like our like client communications. So maybe like there's some backstory here that you didn't have before. So this is what happens when an integration turns on that you weren't expecting and your code does something nasty. This is really bad. This is like, even if you come back up successfully, your application restarts, you get like to the front of the batches lineage, you're still screwed because the traffic is still coming at you. And you need to somehow turn that traffic off before you can come back. Or patch your code, which, as we saw before, takes like an hour. So either you're down for an hour, or you find some way to shut off this traffic faster. And it's great if you can just shut off an IP segment, or like ask the client to stop doing it. But no, you can't necessarily. What if it's like a tag-on-page ad that people are just hitting from their web browsers? When someone can crash your production application from their web browser, it's like not great. And we've had it happen before. So in this case, when someone turns on bad traffic, you also get a flood of emails because your applications are crashing. In this case, I was getting like 60 a second for an hour. So that's awesome, especially when you're crashing faster than you can come back up. You're going to go down pretty quickly and stay there. Load balancers, though, make it fair, so that's awesome. I love it when crashes are fair. So with traffic, like I said, we can't turn back time like with MaxTS, but we need to be able to segregate traffic. We need to make sure that traffic from one integration can't bring down traffic for another integration. So the first thing that is easy to do is to group servers by collection. And this was like a 2010 era thing for AppNexus. Say that you've got integrations with 2 clients, separate their servers out. This creates a problem for capacity planning, of course, because now you need to capacity plan for 2 sets of traffic rather than just 1. But all of a sudden, you're a lot safer. In this instance, we didn't have a collection for this piece of traffic. So at some point, we've got too many integrations to just create a separate group of servers for each type of traffic. And at that point, you need to be able to turn off your code really fast if you can't do something like a networking hack. So in this case, we have feature switches. We basically have the ability to turn off any given handler at any point really fast with a web command. That's only accessible internally, so don't try it. I promise it's only accessible internally. And this is called AN Hook. Paul Kwong gave a previous talk on it, and it basically allows us to turn off code with a single byte write atomically. So you need traffic shaping and segregation tools to be able to survive when you're talking to systems that you don't have control of. The other thing we can do with traffic crashes is if you're working in a language like Java, you have exceptions. And that's great. You do something that you didn't expect, you accept out of it, and you recover somehow. With C, no. You crash. So we have this thing called CORME maybe. And this, given that requests are roughly independent from each other, basically, if a request is going to crash the thread, catches the signal, throws out the request that you were processing, leaks all of its memory, and then returns to the event loop. So you're literally catching the sig-seg-v signal and forgetting about whatever you were processing. This is important because it allows us to stay up even in the case of some traffic is bad. On the other hand, you don't want to turn this on everywhere because you actually want a stack trace if something is bad. So we actually run it on like 80% of our boxes, and 20% will actually crash and give you a stack trace. So you're still going to leak to death, but it's better than being down. Okay, so I've talked about 2 kind of like nightmare scenarios that I was on call for. Most of the time, our system isn't actively conspiring to kill itself. So there's like a lot of smaller degradation scenarios that we deal with on like a daily basis, and I'll talk about a couple of those. This is kind of what I like wake up thinking. A distributed system is only as good as its performance and failure modes because a distributed system is always failing. We have like 6,000 machines that I can go play with right now. Something is always broken, all the time. A rack switch is bad, a hard disk is failing, a memory DIMM is doing something weird, a CPU overheated and melted, something is broken. So all of these systems that I labeled in the diagram above expect that their peers and what they talk to might be broken or down at any point. And it tries to recover. We do pretty well at it. But you need to expect failure of parts of your system as normal operation. The failure of a backing database shouldn't bring down your front-end apps, for instance. Your front-end apps should still start up, even if the backing database isn't there. It might be better if you come up and you're not really processing bid requests totally well, but you're up. And in this case, with regards to degradation, we actually care more about consistency of deadlines than peak performance. So I mentioned that we have a deadline on our auctions of about 120 milliseconds. We care more that we hit that deadline 99.9% of the time, or arrive before it, than we do that one time out of 10 we did it in 5 milliseconds. Like, peak performance is great, but I want to be able to understand and reason about my system. And so here's a graph of bidder timeout percentage. So it's normally like 0, 0.01%. So very small. So this is measuring the rate of timeouts between the imp bus and the bidder, for our bidder. This is something that's really hard, especially because targeting and valuation for the bidder is like a computationally expensive operation. But all of a sudden you see it go to 2.5%, and that's bad for us. That means that 2.5 out of every 100 times we're screwing up. No one's making any money on that auction. And this is bad. So we failed as a consistency mechanism here. Maybe performance is great. All the time this line is 0, but if we can't reason about our system, we're not going to be able to do anything meaningful with it. To this end, some things only happen under load. In this timeout example, consistency failed. We failed to act like a real-time operating system, hit our deadlines consistently. This is the Millennium Bridge in London. I've walked across it. It's really cool. But when they built it, all of the engineering models said it would be great. All of the load tests and like the installation went well, and then they opened it to the public and it started to sway. Like, not just up and down, but like left and right. So people like weren't fans of it, and they realized that it was like moving, a foot to the left and a foot to the right, and so they closed the bridge pretty quickly. And they spent like 2 years putting in dampers, basically shock absorbers, onto the bridge. And they realized that this happened because the bridge's resonant frequency was roughly the frequency at which people walk. And they hadn't figured this out before. So you can't, I don't know if you can test that in a lab or in an engineering model, but certainly they didn't, and it happened when they opened the bridge. And this is pretty analogous to how we find performance issues in production. Like, you can test your code all you want, it can be perfectly correct, and then you throw a million requests a second at it, and it just kind of falls apart. So at some point, you have to test your code in production, you have to test your code at scale. And a load generator can only do so much, because you can only imagine the stuff that's going to get thrown at you, the types of requests, and what an external integration might do, because you don't control that code. So at some point, you have to deal with overload conditions, especially what happens when you've just run out of capacity. It's rare that you're going to be at 150% of capacity, but being at 101% of capacity is pretty likely at some point, even just in burst conditions. So this is what we think about a lot. This is the graph of a latency to read from a database, in particular a user data database in our auction stack. It's, again, normally at 0, and the units are microseconds. So when it hits 100 million microseconds, something is wrong. And this is across a cluster. So 100 million microseconds is 100 seconds, if I've done that correctly. So reading from a database taking 100 seconds when it's a key value store is like not good. It's not great. So this is actually, I dealt with this 3 weeks ago, and I think I know what's going on here now. But basically, this is a single node going wonky and affecting the read and write times for the entire cluster. And this brings up read timeouts for user data, which means that we don't have user data for an auction, which means that the auction itself is less valuable. But it also brings up things like bidder timeouts, because the bidder has less time to respond for the entire auction if it takes longer to read from user data. And this fundamentally is a failure of network flow analysis. Let's imagine for a moment that you've got a router that's talking to some shard, and you can imagine more shards, at a backing provider. In this case, it's a database. If the shard responds 99.9% of the time within the deadline, that's great. If its backing database shard only responds 60% of the time within the deadline, that's bad. you might as well turn this shard off or make this 60%. The performance of your shard is completely determined by the performance of the backing database, especially as you add queues. If you have a single read request out of 100 that must complete before all other read requests can complete, and it takes 100 milliseconds, then all requests behind it are delayed by 100 milliseconds. So queues are the nemesis to consistent performance, especially on a hot path. In this case, losing a single dependency, a backing provider, can bring down essentially the whole shard. And if you have more backing providers, if say this database has to talk to another database, this amplifies itself. You have to multiply these probabilities of failure together. So we try to keep our networks flat. So the impus is the core of our auction platform, and it basically wants to only talk to one level down. It wants to talk to a bidder and get a response. The bidder shouldn't be making any intervening requests, because that compounds the difficulty of analyzing performance. Okay, here's a more pathological scenario. If you've got a router, it's going to be impus, but let's call it a router, which requires data from two sources before it can respond. One source takes 5 milliseconds on the backing database, 10 milliseconds from this source, whatever shard we want to call it, but the other shard is degraded and takes 55 milliseconds from the database and 65 milliseconds from this, then you're going to end up with roughly, let's say, a time of 75 milliseconds to respond, even if only one shard is degraded. So you essentially have to multiply the probabilities of failure together on this. And if we require all of the sources to respond before we can act, errors amplify. And this is something that was wrong with this. Okay, so a single node's bad performance brought down the performance of the whole cluster and basically caused cascading issues. This is a database that should be pretty isolated, and it was bringing up bid request timeouts, so a system that wasn't even connected to it. The answer here might be more sharding. I don't know yet. That is certainly an answer. You can segregate databases or database shards from each other and say that if that shard goes down, I don't require all sources to come back to me before I can respond. I don't have an answer here, but it sucks. So this is fundamentally a result of jitter. One request takes a long time, so the performance of our entire system is degraded. And then one source of jitter is differing workloads. Reads are typically, in most read-optimized databases, faster than writes. If you have reads and writes on the same box, writes may starve reads. And that's bad. That adds latency to reads, and it can be unpredictable. On the other hand, if you have a multi-tenant system, like we do with an auction system, there are many people who might want to run targeting algorithms. If one of those targeting algorithms is expensive, it might delay not only itself, but all of the other members who want to run their targeting. So we try to minimize jitter. And this goes back to, we care about consistency more than we do peak throughput. Okay, so talked about jitter. Clearly, just looking at the max time to respond is useless. We really want to understand more about the characteristics of performance that are causing this. Quantiles. So this is an example of a quantile dump of object sizes. You can imagine it being microseconds of network time, but in this case, it's object sizes. And this is from an app that's running this trace by itself. And really what you care about here is that the minimum object size we saw was 1 byte. The maximum was 14,000 bytes. So this actually gives you a probability distribution for the type of thing you're servicing. If you apply this to timeline, like network data, you can also extrapolate from it. So you see this really long tail where the median response is actually 155, but the max is 14,000. So this is not a normal distribution. The average is probably somewhere around the 75th percentile. And this should inform not only how you expect the system to run normally, but how you expect it to behave when someone adds a lot of large objects or something. It's going to change that distribution and change how you reason about your system. And graphs are going to respond non-linearly. Once you pass some magic limit of performance, everything, timeout rates just shoot up. So that's not great. Okay, so we've talked about data distribution crashes, traffic crashes, performance degradation, and now we're going to talk about just general programming struggles. So this is a chat log of an ad server chat room. In 2014, April, we saw a couple of bidders crash every hour. It'd be 2 or 3 bidders every hour would crash. and we didn't know why. And I took a drink of beer just because I have to think about this. So 2 or 3 bitters would crash every hour, didn't know why. Sometimes like code generation's weird. It goes away with the next update. Like sometimes you try not to think about it and like hope it goes away. Like this was an example of this. This went on for like several weeks. And we noticed that they crashed because they were dereferencing a pointer which was corrupt. The pointer was like into kernel space. Like clearly you can't dereference that. They were corrupt in an interesting way though. They weren't just random. Only the 34th bit was set. Other than that, they were okay. So the pointer was completely fine if you zeroed out the 34th bit. Shit. So, all right, that's clearly something weird. And that's probably not code generation. It's probably not your compiler screwing you. And this is, I mean, they're like joking about this in this chat log, but like it was painful. So we're gonna get back to why this happened in a minute. But this is something that you kind of like only happens in C sometimes, because you're dealing with raw memory access, you're dealing with manual memory management. So C gives us leaks, it gives us corruption, it gives us lack of a standard library. The third one we've kind of solved. There's like I said, 5 core data structures. Keep them simple, test them well, make them fast. Great, done, goodbye. Leaks, we can fix, sort of, by understanding our workload. We use a pool allocator pretty heavily at this point. So allocate memory for a given request into a pool that you've allocated exactly once, free that pool exactly once at the end of the request. So you definitely can't leak any memory. Well, hopefully. Corruption is harder. C allows you to corrupt memory at any point in the request for any reason because you care. And so tooling is helpful here. You guys probably know that Valgrind. Valgrind is too slow for us. If we try Valgrind with production data, we can never start bitter. It doesn't start up ever. It's so slow. I've left it running overnight and bitter doesn't start up. It's not worth it. Something called ASAN, address sanitizer, is great here, and I recommend you all use it. But we didn't have it at the time. This is 2014. So can't use Valgrind. How do we find this? The answer for this one was manual code audit, and a lot of kind of painful hacks like this one. This is actually Paul's code trying to find the source of this corruption. However, the answer here turned out to be our fault, of course. So another chat log from when we found the problem, and Paul says we compare and swap snapshot and a bit shift of the current thread ID over deallocated campaigns, and Mike Wright says, what? It's a chat log. So here's what happened. Event 1, freeze this campaign, but not a timer that was attached to that campaign that was gonna operate on that campaign at some point in the future. Event 2 says, oh, that memory's free, I'm gonna use it because I need to get some memory for this other object. Uses that memory region for a pointer. The timer at some point later fires and says, oh, this is mine, I need this. This campaign is probably still active because I have a pointer to it. It clears the waiting bit of the current thread, which in this case happened to always be the 34th bit, and it goes away, the timer stops. The event clears, finishes, great. Event 2 dereferences that pointer, and the 34th bit is set, and it crashes. And this only happened a couple times an hour because the memory allocation patterns were like so intricately complicated and like not common. So Paul says, explains a little bit more, budget wake up for long deallocated campaigns. We basically spin lock on in-pacing sleep by clearing out the thread's bit. And Sen says, you should be drinking, which is what we did. So someone asked me at one point, like, what I'd learned at AppNexus about distributed systems. It is understand your workload, reads versus writes, be able to characterize what's gonna happen on your system. At any point, be able to observe what's happening on your system because your mental model of the system may not match reality. Be able to partition your workload and specialize parts of your system for that workload. So segregate traffic from each other, segregate applications that have different workloads from each other. Keep your network flow graphs flat because otherwise you multiply your probabilities of screwing up. Use every possible feature of your environment to your advantage. That means if you're in C, like yeah, use signal handlers because they will save you. Even if you're gonna crash on a seg fault anyway, signal handlers can save you. And find a way to replicate prod, even if it means testing in prod. At some point, you have to load test in production, because you're going to deploy it to production anyway. So just at some point you have to get it to prod. So all of the stuff that I've said about our platform with regards to unreliability may make you think that we're like pretty unreliable. Turns out not to be the case. Last month we did 4 nines of uptime, which is about less than 1 minute down for the entire month. The previous month we were 100% up. We were not down for a single second of the entire month. The 3-month rolling average is not as great, but it's improving. 3 nines there and a 6, so we can round it up to 4 nines. So 4 nines of uptime is basically where I want to be, though, and an 8. So that's all I have. I'll take questions. There's a mic over there if you've got questions, so please use it.
I don't think this is terribly large in the scheme of all the deep existential pain you deal with every day, but I'm just curious. Is there some particular reason you're using MySQL over Postgres, or is this just some decision somebody made while they were drinking?
Kind of the latter. It's really because we started this database in 2007 and Postgres either didn't exist or wasn't mature enough, or it's because MySQL was just like the thing you used. We've begun a slow migration, I think, to bigger and better things. We're actually not using MySQL vanilla version. We're using MariaDB, which is slightly better, but not as great as Postgres. So we're getting there.
So when you were talking about like the shard not being able to talk to the database when it was causing a timeout, why don't you just drop like the responses that take too long?
So yeah, you can do that. I can actually rewind to that slide. Okay, so in this case, I mentioned that this gets worse as you add queues. In this case, if this shard is processing things in order, then it might wait the maximum deadline for that given request to come back, and say that's 10 milliseconds. If you really want things in a 1 millisecond, then you've potentially timed out 10 requests behind that one request. So it kind of compounds as you add queues, if that makes sense. All right, thanks everybody.